Imagine a place in space-time that only spits things out, never lets anything in. This is the idea of a white hole. In general relativity, a white hole is a hypothetical region that cannot be entered from the outside. Unlike a black hole, nothing can fall into a white hole, but energy, matter and light can escape. White holes appear in the mathematics of eternal black holes, the maximally extended solutions. Those solutions contain both a black hole region in the future and a white hole region in the past. From the white hole interior, material emerges. Light and information shoot outward. But you could never fall in from outside. The horizon is one way outward. Important caveat: white holes don't form via normal stellar collapse like black holes. They arise only in idealized eternal solutions, not in realistic collapse scenarios. Stephen Hawking argued that, in thermal equilibrium, a black hole's time reversal is a white hole. So mathematically, emissions from a black hole link to the emissions you'd expect from a white hole. The maximally extended Schwarzschild spacetime has 4 regions, 2 exteriors and 2 interiors. It looks like 2 universes linked by a bridge, with a white hole on one side and a black hole on the other. This bridge is the classic Einstein-Rosen wormhole, a geometric connection in the extended solution. But you cannot use it to travel between universes. The horizons are one way. Historically, some thought quasars might be white holes. Now we know quasars are powered by supermassive black holes. There's no observational evidence for white holes in modern astrophysics. White holes would be highly unstable. Any small and falling matter could stop the white hole's emission. There's no known astrophysical process that reliably makes a white hole. Properties: mass, charge, angular momentum, like black holes but time reversed. You can imagine charged or rotating white holes. Each maps to specific solutions. White holes are non-deterministic. What emerges can't be predicted from outside data alone. That breaks the usual predictability we expect from physics. So far, a mathematical possibility, not a physical certainty. Next, the history and bold hypotheses that connect white holes to the Big Bang. The idea goes back to the 1930s with Oppenheimer and Snyder exploring solutions of Einstein's equations. Later, Novikov and others formalized the white hole concept in the 1960s. The maximally extended Schwarzschild metric requires both a black hole and a white hole region to be complete. Geodesics show particles can emerge from the white hole horizon in the past. If you add collapsing matter, a realistic black hole history, the white hole interior disappears from the diagram. That's why astrophysicists treat white holes as mathematical artifacts, not formed objects. Hawking suggested that thermal equilibrium is time reversal invariant, linking black hole and white hole emissions. In a formal sense, emission from one maps to emission from the other. Some modern proposals go further. Could white holes connect to baby universes or the Big Bang? We'll explore those provocative ideas next. Stay with us. The theory gets stranger from here. History and hypotheses, coming up. Next, detailed historical context and speculative links from black holes to new universes. Let's continue. Oppenheimer and Snyder first explored gravitational collapse solutions in the 1930s. Those early solutions opened the door to thinking about time-reversed geometries. Later, Novikov and Kardashev developed the idea further in the 1960s and 70s. They placed white holes firmly in the catalog of mathematical solutions. Eternal solutions exist forever. Real black holes form at finite times from collapse. Add realistic collapse, and the white hole region disappears. Some researchers have proposed bold ideas. What if the Big Bang is a white hole-like event? In that view, our universe could be the interior of a black hole in a larger space. The Einstein-Cartan theory adds torsion to spacetime. Spin interactions can prevent singularities. Instead of a singularity, the collapse rebounds, forming a new expanding region. Shockwave cosmology models the Big Bang as an explosion inside a black hole, a small bang that becomes a new universe. Some have even suggested certain gamma-ray bursts could be white hole events. A few studies proposed identifying anomalous GRBs with white holes. Intriguing but unconfirmed. Most astrophysicists remain skeptical due to lack of evidence and formation problems. In charged or rotating solutions, a white hole can act like an exit door from a connected black hole, a wormhole. But such passages are not usable for travel. Causal constraints and instabilities prevent safe passage. Types: non-rotating Schwarzschild, charged Reisner-Nordstrom, rotating Kerr. Each has distinct structure and theoretical implications. Even tiny perturbations can render a white hole unstable, turning the region into something else. That's a major reason white holes are not favored as real astrophysical objects. Quantum gravity and ADS-CFT treatments reproduce time reversal arguments, supporting formal reciprocity. But a full quantum description of white holes remains speculative. Hypotheses. 1. Time reversal symmetry produces white holes. 2. Links to Big Bang or baby universes. 3. Short spontaneous small bang events possibly visible as GRBs. Takeaway: white holes are mathematically allowed, but lack formation mechanisms and are unstable. No robust observational evidence, so most scientists treat them as interesting math. Myth: quasars are white holes. False. Myth: wormholes let you travel universes. Not in practice. Reality is more constrained. Still, studying white holes probes deep questions about time, quantum gravity, and cosmology. Speculation can point to new physics even if the object itself is unreal. Recent work has revisited white hole ideas, sometimes linking them to observed phenomena in creative ways. These remain provocative but unconfirmed. Summary: allowed in theory, not formed naturally, not observed. Mathematics and observation are currently at odds. If white holes existed, we'd search for transient, unrepeatable bursts with unusual signatures. Look for one-time signals unlike ordinary astrophysical events. Whether real or not, white holes expand our thinking about space, time, and origins. They are a reminder that the equations of general relativity still hold surprises. If you enjoyed this deep dive, like and subscribe for more cosmic explanations. Thanks for watching. See you next time. White holes, math, mystery, and a window into what we don't yet know. Keep questioning, keep exploring, subscribe for more.